that would give us this. It's also important to be able to go straight from here to the product, but it's good. It's really important to know this mechanism.
The one that's going away from.
This is going away from us, and this is going into the board. This particular problem, it turns out the stereochemistry doesn't matter, but the two bromines will be on opposite sides because this bromine has to attack from the side opposite to where the first bromine is because of steric hindrance. So let's see. Where are we? All right, so this is the right way to put in the two bromines. That's right. All right, and now we need to do an elimination. Can we see anything here that might give us an elimination?
We need a bulky base, right?
You might think that. None of these bases are particularly bulky.
Right.
What type of carbons do we have here in our alpha carbons? Primary, secondary, or tertiary?
Secondary.
Secondary.
So just any.
This already has a lot of steric hindrance from the substrate, so the base doesn't have to be bulky. In fact, if you look at the SN2 handout, you'll see that if you use a strong base and the SN2 handout, you get an E2.
Yeah, so
If you use an O minus or an N minus, you're going to get an E2, even if it's not bulky. Even if we look at the non-bulky base column, once we're in the secondaries, we're going to get an E2. Well, who do we have here that's a strong base?
K.
Yeah, who else? So K has an O minus. That's good. Who else here is a strong base? Who are the elements that give us E2 reactions?
Well, nitrogen. Nitrogen?
Yeah, not a neutral nitrogen, but a negative nitrogen. So where else here do we have a negative nitrogen?
E.
Yeah. Now it should be very apparent that that's a negative nitrogen even though they didn't put in the charge because it's bound to a sodium. Anytime you're bound to a sodium or a potassium, you're in an ionic bond and you're going to have a negative charge. That's the same way we know that this is an O minus because it's bound to a potassium. When you're bound to potassium or sodium from the first column, that's an ionic bond and you have to draw in the charges yourself. This is actually an even better base than oxygen is. It turns out that for making alkynes, we generally use N minus, so we simply need to memorize this. We need to memorize that the way to make alkynes is to use N minus. Because we need to do two eliminations in a row, and this is an even better base than the oxygen. All right, so we should do E. And this gives us some more practice drawing E2 reactions. So let's draw the mechanism for an E2 here.
I don't understand how you get rid of the second bromine.
Well, let's get rid of the first one first. So let's start by doing an elimination reaction.
When you do, does the NH2 just go over there? Oh, you're right. I always make that mistake.
Oh, because then it becomes NH3.
What do you say, Shilpa? Does the NH2 just go over there?
Well, I was trying to figure out what's attacking. Sarah's got the right thing attacking. NH minus, and then it picks up a proton.
Mm-hmm.
And this bond breaks to form a
Good.
double, and this guy leaves, right?
Good. Who leaves?
Well, the way I have the arrow, I don't show it leaving. I'm taking an electron with it, so I'm confused.
Yeah, it looks like you might be forgetting a little bit what happens in an E2.
I'm sorry, I don't know what to do. Can you show me what to do?
So let's
Oh,
see
so
here.
we formed one bond, and then it does it again.
Now this is going to act like a base. What do bases do?
Oh, I got it.
They take protons from the beta carbon. So I'm going to start by treating this like the alpha carbon and this like the beta carbon.
I got it. So I guess this shares its electron, this takes the hydrogen, and this leaves. It's the three arrow thing. The three arrows always gets me. Because I'm thinking there should only be two at one time, but.
And then it does it again. And makes the alpha.
Yeah, I think we got that.
So why does it go for that H and not the H that's on the alpha?
Well, in an E2, you have to attack both the beta carbon and the alpha carbon. the beta carbon loses a proton, and the alpha carbon loses the leaving group. Otherwise, you can't form a pi bond.
They're
between the
both alpha
elements.
at one point.
That's right, so you have to focus on who you're treating as the alpha carbon first. If we treat this like the alpha carbon first, we should treat this like the beta carbon.
Can that floating BR now grab the other H?
One sec, sorry.
That's a good question. So then this BR goes with that and then it's an NABR.
That's what she's asking, like who picks up what? Like whether it becomes HBR or NABR or
Okay, so in the first step here, we've taken this proton and we formed a new pi bond between the alpha and the beta carbons. And let's see, I should have said that we still have this bromine here. Good. So now, does that first step make sense?
Yeah.
All right. Now we should do the next step, which should be quite similar.
So you're getting NABR and ammonia each time.
That's true.
Yep.
Yeah. So let's see. Now, this will be the alpha carbon. Nope. Oh, I got the bromine in the wrong place. That
Or
is-
if we have a hydrogen, then the NA would have to work out.
So now this will be the alpha, and this will be the beta carbon. That's right.
Yeah, that makes sense.
Yeah, that's what I have, except the opposite of the same thing. I just took the other.
Okay, and now we should take this beta hydrogen
Yeah.
and take that bromine. And we don't need to draw anything else because this is what we're going to get out of that.
So we're just, it's leaving because the hydrogen's forming a bond and it's forcing it to leave kind of thing?
You mean the bromine is leaving?
Yeah.
Because, yeah, the bromine is leaving because it's getting kicked off by these electrons. And these electrons were freed when we took this hydrogen. And this hydrogen was taken because we have a strong base. The base is taking the hydrogen, that frees these electrons to form a new pi bond, which forces off the leaving group. So you can see we did need two leaving groups. We needed two leaving groups because we were going to do two eliminations, since we started with an alkane here. I wouldn't worry too much about this mechanism in this particular case. It's important to know how to do E2s, but this is a kind of confusing E2 because we're doing two in a row. The important thing is to see that we have to do two E2s. I'm not worried too much about the mechanism here. All right, so let's review the key points here. This is a good problem to do synthetically again. You should say to yourself, what am I making? I'm making an alkyne. And you guys have basically learned one way to make alkynes out of non-alkynes. The only way you've learned how to make an alkyne out of a non-alkyne is by this E2 elimination. This is the only way you've learned how to do it, by E2 elimination. And that means you have to start with an alkane with two halogens on adjacent carbons, because you have to do two eliminations in a row. So as soon as we see that we're making an alkyne out of a non-alkyne, we know that we're going to be attacking a dihalogen. And we simply need to memorize that this is the base that is customarily used for making alkynes. Normally we use LDA or tert butyl oxide, but this is the standard base that is used for making alkynes, sodium amide. Now this is very typical as well. Notice that how do we make an alkene into an alkyne? Well, we don't go directly there. Instead, we start by putting in the halogens.
And actually removing the bond and then.
That's right. So there's a little bit of backward thinking here. First, we have to put in the two halogens. Why do we need two halogens? Because we're doing two eliminations. And fortunately, we know a good way to put two halogens on adjacent carbons, which is to have Br2 attack an alkene. So this is an important reaction to put in your notes. We haven't talked much about alkynes today, but this is a reaction you're expected to know how to make alkynes. You do it with two E2 eliminations in a row.